Okay, hi everyone. Today we're going to look at the last part of exercise 12C, which follows on from 12C part 3. In 12C part 3, we created recurrence relation models and rules to determine predictions, where things would be located after a certain period of time, using transition matrices and an initial state matrix as well. One of the keys about 12C part 3 was that the numbers didn't change over time. All that changed was the breakdown of where things were located. So, for example, the problem that we looked at with the cars in Bendigo and Colac, there were always 90 cars. It's just that the breakdown of how many cars were in Bendigo and how many cars were in Colac, that changed over time, but there were always 90 cars. There were 90 cars to begin with, 50 in Bendigo and 40 in Colac. And no matter where they transitioned to, there were always only 90 cars present. So in 12C part 4, we're going to look at more complicated situations where over time we're either adding to the total number of cars or items or whatever it might be, or we might be reducing the number of cars or items. Okay, so in the case of a car rental company, they might purchase new cars on a regular basis, so they've got more cars to rent out. Obviously, that changes our model because our model so far was only able to suit a fixed number of cars. So we're going to have to look at how we can modify our techniques for this type of problem. So I'm going to share the notes for 12C part 4, and we'll do a couple of examples as well. Okay. So far we've considered matrix recurrence relation models of this type. We did that in 12C part 3. Okay. And we looked at a couple of examples of that. However, if we want to, so as I said, we looked at the situation where there were 90 cars available for rent in those Bendigo and Colac branches. What happens if management wants to increase the total number of cars available for rent by adding, say, an extra car at each location each week? Well, then our formula needs to reflect that increase in number of cars. So what we do is we end up with a model, a recurrence relation model that is a little bit different. We've got an extra bit at the end, which is an extra matrix added or subtracted. Okay, so we've still got our initial state matrix, which is still called S0. Most of the recurrence relation looks the same, except we've got this extra bit added on at the end. Now, if you think back to financial problems in our previous module, this is a situation where we've got both geometric and linear components to our recurrence relation. And hopefully what you remember back from that, so when we're looking at reducing balance loans, for example, or annuities, is we weren't able to construct a rule to allow us to figure out the value after a certain period of time. All we could do is a step-by-step approach using our recurrence relation model. And that's what we're going to be forced to do here as well. So if I know my starting matrix, my initial state matrix, and if I know my transition matrix, and even if I know this matrix B that's been added on, I'm not able to work out S5 until I've worked out S1, S2, S3, and S4 in between. Okay, you cannot go straight from S0 to S5 because there is this geometric and linear component together, which causes problems when we're trying to create a rule. But our recurrence relation will still work perfectly well, just means that we're going to need to do step-by-step calculations all the time. So for example, 14, same situation with the two car rental branches, Bendigo and Colac, same initial state matrix, same transition matrix, except in this case, the management is going to purchase 2 extra cars to add to each branch each week. So every week, there are going to be 2 more cars added to the Bendigo branch and 2 more cars added to the Colac branch. That means the matrix that I'm going to add will be a 2x1 matrix, 2 and 2, because I'm adding 2 to the Bendigo branch, that's the 2 at the top, and I'm adding 2 to the Colac branch, that's the 2 down the bottom. Now, if we were reducing the number of cars, then my matrix B would have some negative numbers in it. If I was removing a car from each branch each week, 1 car from each branch each week, then the numbers would be -1 and -1. The top -1 would be reducing the number of cars at Bendigo by 1, and the bottom one would be reducing the number of cars in Colac by 1. So this is what we've got to work with. I've got an extra matrix that I'm going to have to store in my calculator, and then we're going to determine the number of cars at Bendigo and Colac after 1 week and then after 2 weeks. So I've stored my T and S naught matrices already. Matrix B is a 2x1 with the numbers 2 and 2. I'm going to store that as matrix B. Now, we already know what S naught is. We want to work out the number of cars at each location after 1 week. So my rule is I've got to do T times S naught plus this new matrix B. Okay. Now what we notice, importantly, is that the total number of cars at the 2 branches combined adds up to 94. Okay, we started with 90, now we've got 94. That's because we've added an extra 2 cars at each location. That's a total of 4 more cars added to the company's fleet. Okay, so after 1 week, there will be 46 cars in Bendigo and 48 cars in Colac. Now, if I want to work out the value after 2 weeks, what I can do is store this new matrix as S1. Okay, that was the numbers after 1 week. And now I can do T times S1 plus B. I've got to add B every single time. Okay. And now we get 43.6 and 54.4. Now, if I was to add the totals together, I get a total of 98 cars, another 4 cars up from the previous week, because again, we've purchased 2 extra cars at each location. Okay, and that's going to continue. The numbers in my matrix from S1 to S2 to S3, there's always going to be 4 extra added in total every week. Okay, so this is my S2. That means that after 2 weeks, there will be, if I round to the nearest whole number, 44 cars in Bendigo and 54 cars in Colac. Okay, so you can see that we've got our answers. That's after 1 week. You can see the calculations that have been shown in the answer, and then a very definite worded answer there. And then after 2 weeks, again, I suggest that we probably round our worded answer to the nearest whole number, but definitely leave a decimal place in our matrix answer, 43.6, 54.4. But as a worded answer, I'm happy for you to put 44 cars in Bendigo and 54 cars in Colac. Okay. So we've got a question from the notes, and then I'll do one from the textbook as well. So we've got a new transition matrix. This is example 1. We've got a new transition matrix and a new initial state matrix. So I'm going to store them. So my new initial state matrix was 100 and 100. I'll store that as S0. Okay. And my new transition matrix was 0.4, 0.6, 0.4, 0.2, 0.8, 0.6, 0.4, 0.2, 0.8. I'm going to store that as matrix T. Okay. So the first part of the question actually doesn't require any matrix to be added at all. Okay, this is just similar to what we were doing in 12C part 3. It does say to use the recurrence rule. All right, so I'm not allowed to use the shortcut rule. I'm not allowed to use T to the power of N here. I've got to do it step by step. So to find S1, I do T times S0. And that's the value of S1. S1 is 80 and 120. I'm going to store that as S1. I'm then going to go and use that in my next calculation. To work out S2, I'm going to do T times S1, and that gives me S2. So this is S2. I'm going to store this as S2. And I think the question wanted me to find S3, so it did. So one more thing to do, I've got to do T times S2, and that's S3. So S3 is 68.8 and 131.2. Now, importantly, in this question, there's no practical application. It's not like these are people or cars or chickens, right? They are, it's simply numbers. We've got no practical application. So there is no reason for me to round to the nearest whole number, okay? In the other questions, we've only rounded to the nearest whole number because it doesn't make sense to have a fraction of a car or a fraction of a person, okay? But in this question, we don't know what these numbers refer to. So we will certainly keep our final answer, even a worded answer. I would say S3 is 68.8 and 131.2 as that 2x1 matrix. Okay, we probably can't put a worded answer because we just don't know what these numbers refer to. But certainly when we're writing down matrix S3, do not round off at all. Okay, keep the decimal places. Okay, now we're going to use the recurrence rule with the R added on at the end, where R is this 2x1 matrix, 10, 5, to determine S1 and S2. So I'm going to store 10 and 5 as matrix R. Okay. And I've still got T and S0 stored in the calculator, so I can still use them. So we want to work out S1 first. So my rule says that S1 is going to be T times the previous state, which is S0 plus R. So T times S0 plus R. T times S0 plus R. Oh, little lowercase r. T times S0 plus R. There it is there. So this is matrix S1. All right. Now I'm going to store that as matrix S1 because I'm going to need to use that in my second calculation to find S2. All right. So we've already found S1. Part 1's done. S2 is going to be, if we use the rule, S2 is T times S1 plus R. Just one step at a time here. So T times S1 plus R. And this is the matrix for S2. Okay. So 89, 141. Good. You notice that the numbers in matrix S0 added to 200. In S1, they added to 215. And in S2, they added to 230. That's because we're adding a total of 15 each time. 10 and 5 adds up to another 15. We're adding a total of 15 each time. Okay, so they're the questions from the notes. I've just got one question from the textbook to do. On Windy Island, seabirds are observed nesting at 3 sites. We've looked at this situation before, A, B, and C. The following transition matrix and transition diagram can be used to predict the movement of seabirds between these sites from year to year. Okay. Notice that in our transition matrix, from A to A is 100% or 1.0. From A to B is 0, from A to C is 0. That means that any bird that is nesting at site A one year will remain at site A the next year. Okay, once they're there, they stay there. That must be a very nice nesting site. However, you can see from the other columns that birds that were at site B, some will go to site A and some will go to site C. Most will remain at site B, but not all of them. And the same thing with site C. Most will remain at C, but some will transfer across to A and B. But the important thing is that once they're at A, they stay at A. So over time, there's always going to be some movement from B and C across to A, but never back the other way. Okay, that's going to become important shortly. So initially, 10,000 seabirds were observed nesting at each site. So that's the value of S0. And I'm going to store these matrices. Bear with me while I put this transition matrix in. So we're going to have 1, 0, 0. 0.1, 0.9, 0.1. And, oh, sorry, that doesn't add up to 1, 0.8. And 0.05, 0.05 and 0.9. There we go. So I can put these to 2 decimal places, but we know the calculator is going to change it back anyway. I'm going to store that as matrix T. And initially we had 10,000 birds at each site, so this is going to be a 3x1 matrix this time. 10,000, 10,000, 10,000. Store that as matrix S0. Okay. Now, use the recurrence rule to determine S1 and to predict the number of seabirds nesting at site B after 2 years. All right, so after 1 year and after 2 years. At this stage, I'm not adding on any extra birds after each year or subtracting any birds after each year. So S1, quite simply, is going to be T times S0. There we go. That's how the birds are arranged after 1 year: 11,500 at site A, 8,500 at site B, 10,000 at site C. I'm going to call that S1. And then to find S2, I've got to do T times S1. Okay, one step at a time. There we go. These are how the birds are located after 2 years. 12,850 at site A, 7,300 at site B, 9,850 at site C. So the question that said, predict the number of seabirds nesting at site B after 2 years, that is the middle number in matrix S2. So that's 7,300 because this is my S2 matrix. Okay, T times S1 will give me S2. Okay. Without calculation, write down the number of seabirds predicted to nest at each of the 3 sites in the long term. So this is after we have reached steady state, and then explain why this can be done without calculation. Now, this is where it's really important that birds, once they're at site A, they never move to any other sites. So eventually, even though it will take a long time to happen, all these other birds that are at sites B and C will eventually move to site A, because once they're at site A, they stay there, okay? And there are always some birds going from B to A and some birds going from C to A, but never in the other direction. So eventually, it might take many years, but eventually all of the birds are going to be located at site A, which means all 30,000 of the birds are at site A and 0 birds will be at site B or site C. Okay, so this can be done without calculation because 100% of the birds that are at A will stay at A and 0% of the birds at A will move to other sites. Let's just check that on our calculator. T to the power of 50 times S0. You can see that it's going to take a long time to get to steady state. T to the power of 51 times S0. And you can see that we haven't reached steady state yet. Okay, there are still birds transitioning between the 3 different sites. However, what we're noticing is that site A is definitely getting bigger. Okay, so obviously 50 and 51 didn't work. Sometimes that's going to happen. So I'm going to try a bigger number, T to the power of 100 times S0, and T to the power of 101 times S0. T to the power of 101, move your cursor across, times S0. Okay, now we're getting much closer to steady state. There are very few birds at sites B and C, 7 and 20 if I round to the nearest whole number, and that even changes for the next year. But we haven't quite reached steady state. The numbers are still changing. Let's do T to the power of 500. And T to the power of 501. Okay, now you can see that it took a long time, but we've eventually got all 30,000 birds at site A, no birds at site B and C, okay? But we could have figured that out based on the 1 and the 0 and the 0 in that column. Okay, to help solve the problem of having the birds eventually all nesting at site A, the ranger suggests that 2,000 seabirds could be removed from site A each year and relocated in equal numbers to sites B and C. So this is our new recurrence relation where we've got this N matrix added on. Okay, it's very similar to what B was in the previous examples. And you can see that each year, 2,000 birds are subtracted from site A because they're removed from that site, and we're adding another 1,000 to site B and C. Now, notice that because negative 2,000 plus 1,000 plus 1,000 adds up to 0, our overall number of birds will remain fixed at 30,000, okay? Because some birds are being moved, the birds are being moved from one site to another, but we're not actually removing birds completely or adding any extra new birds. Okay, so if we want to evaluate these transitions, then S1 is 10,000, 10,000, 10,000. So I'm going to store that as S1 this time. All right, just got to be a little bit careful that that's now called S1. So it is still a 3 by 1 matrix. And I'm going to 10,000, 10,000, 10,000. And I'm going to store this as S1. T, just check that's still correct. Yes, it is. And I've got to input matrix N, which is a 3 by 1 matrix. Negative 2,000 from site A, adding 1,000 to site B, adding 1,000 to site C, and we're calling this matrix N. Okay. So S2 is going to be T times S1 plus N. T times S1 plus N. That's my matrix S2. Okay, so now we've got 9,500 birds at each of the first two sites and 11,000 at site C. If I store that as matrix S2, I want to reuse that number again. To find S3, S3 is going to be T times S2 plus N. Okay, so T times S2 plus matrix N. Now this is the breakdown between the three sites. Okay, and I also want to work out what S4 is. Okay, so I'm going to have to store this one as S3. So every time I get a new state matrix, I'm storing it immediately so that I can use it in the next calculation. So my last calculation is T times S3 plus N, and this will give me S4. So that's how many birds are at each location after, 4 years. Yep, S4. Okay. In terms of giving your answer here to the nearest whole number, this is a little bit awkward because you've got a 0.5 and a 0.5. So perhaps even in your worded answer, just in this situation, write it as 8,507.5 birds at site A, 8,912.5 birds at site B, and 12,580 birds at site C. Okay, just because the 0.5 and the 0.5 make it really awkward for rounding. Okay, so hopefully that makes sense. That's the end of matrices, and that's the end of 12C. So these will all be put on Classroom, and please make sure that you watch them. Thank you. See you next time.